This video is about theories and progress in science. Here is an idealized form of theory formation in science in chronological order. First, systematic observations. Scientists observe phenomena, recording them as well as possible. The observations are done in a systematic, pre-designed manner. 2. Classification or categorization of the observations. Scientists try to group the phenomena according to features they have noticed. 3. Hypothesis formation. The observed things may be called facts, and it is important to remember that, as the Latin root of the word suggests, they are handmade. They do not just exist out there on their own, but facts that are considered relevant are picked out by the scientists who try to explain them. Possible explanations for the phenomena or facts are suggested and tested. A hypothesis is a testable claim, a prediction of what should happen if the assumptions made are correct. 4. If possible, laws or regular relationships between or patterns of phenomena may be abstracted. Also, models of the phenomena in question may be designed. And finally, 5. A theory is formed to explain what is going on, why the possible law seems to hold. Further hypotheses are inferred from the theory and tested, adding confirming or disconfirming evidence for the theory. The most important thing to understand here is that a theory is not just some guess, as the word is sometimes used in non-academic speech. It is a deep explanation of a phenomenon or a feature of reality. It is not just a theory, as sometimes some anti-science propagandists use the word. A theory may or may not be true, and even if scientists widely consider it to be true, as is the case with the theory of evolution through natural selection, for example, the theory is still called a theory because that is what it is. The same way, any proposition P will remain a proposition regardless of its truth value. Truth value just describes the status of P. I already explained the basics of deductive and inductive logic when discussing epistemology. There is another suggested type of logic that has to do with science, called abduction. It does not mean something like kidnapping or people being taken away on flying saucers. Abduction or abductive inference or reasoning is usually understood to mean inference to the best explanation. And it is thought to be how scientists think. The idea is that to explain why something occurs, one should look for the best explanation for it. If you see a soccer ball rolling across the street, it may seem reasonable to think that a person, probably a child, has kicked it. The logic can be expressed as follows. 1. If a child kicks a ball, then the ball will roll over the street. 2. The ball is rolling across the street. 3. A child has probably kicked the ball. Abduction from 1 and 2. You may now notice that this is actually the logical fallacy known as affirming the consequent. There could easily be other explanations for the ball rolling across the street, such as being blown by the wind or because it fell from a rooftop due to rain and bounced toward the street, or any other. But that is why the word probably was used in the inference. Perhaps it should be possibly instead. But out of the scenarios I just imagined, the one involving a child may seem most likely. This kind of thinking then requires much use of imagination and some ability to assess the likelihoods of different scenarios. Another model of how scientists are thought or supposed to think is called the hypothetico-deductive model. The idea is that scientists make a conjecture or hypothesis about what could be an explanation for the phenomenon they are trying to explain. Then they deduce predictions that should follow if the hypothesis is true. These predictions are then tested experimentally if possible, but the idea is to look for disconfirming evidence, something that contradicts the hypothesis. Such evidence would refute the hypothesis, while confirming evidence does not prove it, because it is a fallacy, as I just explained. As long as no disconfirming evidence is found, other deductions about predictions need to be made and tested. This model does not allow a hypothesis to ever be verified, but surviving many attempts to disconfirm it sure makes it look appealing. The logical empiricists of the Vienna Circle from 1924 to 1936 had academic discussions and, among other things, tried to find a criterion for science. They thought that verificationism would do. That was the idea that in order to be scientific, a theory would have to be such that it can, at least in principle, be verified, shown to be true, somehow. Karl Popper, who was in contact with the circle, realized that verificationism doesn't work. He proposed falsificationism instead. The idea that in order to be scientific, the theory must be such that it can, at least in principle, be falsified, shown to be false, somehow. He fully embraced the idea that there is no certainty in science, and any theory that seems to be true now may later turn out to be false, and that, he thought, is what makes science special. Of course, it turned out to be more complicated than that. It is not as easy to prove a theory false as Popper thought. Later philosophers of science have mostly thought that it may be impossible to prove a theory true or false. Instead, theories can only be tested. As I have already said earlier, those tests provide evidence that either supports the theory or counts against it. Thomas Kuhn wrote a much-discussed book titled The Structure of Scientific Revolutions, where he argued that science does not actually progress slowly and steadily, but rather through scientific revolutions or paradigm shifts. According to him, there are phases of normal science, where perhaps some steady progress is made under one paradigm. That includes a way of doing science and the basic concepts used in the field of study, in general, the basic framework of the science. The big changes, such as the switch from geocentrism to heliocentrism in astronomy, requires a revolutionary change or shift of the paradigm, in this case the Copernican revolution. Kuhn thought that paradigm shifts are so huge that they require the change of the generation of scientists. The older generation of scientists will not change their minds, but a new generation can embrace the new paradigm. Because the competing paradigms are incommensurable, they cannot be rationally compared to see which is better. Kuhn's views are not accepted as such, but they certainly have been discussed a lot. An interesting example of change in scientific theories is how Einstein's theory of relativity, or of the constantness of the speed of light, refuted the ether theory. It is sometimes said that Einstein also falsified Newton's understanding of gravity, but others have explained that instead of falsifying Newton's theory, Einstein's theory subsumed it. Newton's theory can be seen as an approximation of Einstein's theory of relativity. It works nicely within certain parameters, but not outside of them, which is where Einstein's work is needed. In my next video, I will talk about the differences between science, pseudoscience, and also about ethics in science. See you then.